So now we're going to spend some time looking at an idea called electronegativity, and we shall define electronegativity to help us with this particular lesson. So here we go.
So when a bond is formed, electrons may be gained, lost, or shared. We're actually interested in the sharing one now. Like this. So there's a bond where electrons have, the bond is representing electrons. So the sharing is not always equal between the two atoms. It is possible for one atom to pull the electrons in the bond closer to itself and thus gain a negative charge. So that AB, what we're saying is that B was actually better at pulling those electrons towards it. So you can see this funny little shape right here that is representing the negative end of the molecule because these electrons are negative and they move towards that end. And then over here we've got this funny little sigma, and it's a plus. Now what's that representing? Well, what we say is a dipole has been created. And what a dipole is it's just, well, what we use is arrow to represent the dipole, and the arrow points to the negative end. So you can see that this end is pointing towards the negative B end, and then this to me looks like a little plus sign, so that's how I remember that that's the plus end, and that's a dipole. And a dipole is just a molecule that has a positive and negative into it. So we can have some of those attractive forces like what we just talked about back in our crystalline structure. So electronegativity, this is the official definition, is a measure of the tendency of an atom to attract a bonding pair of electrons. Again, it's about attracting those electrons towards itself. Here's a little picture of the periodic table because all these electronegativities are listed on here. So I'm looking at hydrogen, you'll see the H, and there's this 2.2 right above it. That represents how strong hydrogen is at pulling electrons towards itself. Lithium has a little 1 over it, so it's getting weaker. Sodium is even weaker. So actually we've got a trend here. We've got our electronegativity decreasing down the group. If we go across here, and I'm just going to start with titanium here, it goes 1.5, 1.6, 1.7. It's generally going up. It's not an absolute pattern, but it does seem to increase this way. If you look over at group 8 elements, they are happy. They're stable. They don't want to pull in electrons in a bond because they don't even form bonds, so they don't have an electronegativity. So the atom with the greatest electronegativity is actually right here, fluorine. It's got a number 4. That is the highest one. So you can see the halogens are all pretty good at attracting electrons in the bonds. Now we're going to need these numbers in a second, and they're going to help tell us what kind of bonds form in a compound. Good, so to determine what type of bond is present in a molecule, you only need to subtract the two En values, the ones we just talked about, and you always take the larger one and subtract the smaller one, so it's always above 0. And what we're going to do is we're then going to place this number on our answer on this number line, and this number line it's like not exactly carved in stone. So we've got 0 on one end, and we have 1.7 in the middle, and then kind of every other number above. And even this 1.7 can sort of, it's not an absolute number, it can kind of move around, but it's just sort of a ballpark idea. It's going to help tell us what kind of bond we've got going on. So once we've subtracted, if we end up with a result of exactly 0, what we've discovered is that we have a pure covalent bond. There is no sharing of electrons in this molecule, so it doesn't have a plus or minus end. It's just kind of like a neutral molecule. So that's like maybe our simplest one. Now the most interesting range is going to be this range here from 0 to about 1.7. So when you subtract and you get a number in that range, it's going to be what's called a polar covalent bond. This is really what electronegativity, this whole lesson is about. It's really about this particular one. So what this means is that electrons are not shared equally in a bond, and a dipole exists. So that dipole I drew on one of the previous slides, that would be a polar covalent molecule, or a polar covalent bond for that molecule. Now the last result is anything kind of above 1.7, and this isn't that interesting because we just end up with a regular old ionic compound, and we probably know it's an ionic compound just by looking at the fact that it's a metal and a non-metal. We wouldn't need to do this En, but it would just be a good way to sort of confirm it. So let's wrap this up with some examples. What type of bond exists when the following atoms combine? So NaCl. So if I give you this one, and again you're looking at it, you're like, okay, it's a metal and a non-metal, it's obviously ionic, but now we can go ahead and prove it. So you go to your periodic table, grab it, look up the En for sodium, and it's 0.9. You do the same for chlorine. It's 3.2. So we're going to subtract those two values. So our answer should be 2.3. So if you go back to our number line, it's going to solidly place us in the ionic range, and we've confirmed that sodium chloride is in fact ionic. Not that interesting. B, oxygen gas, O2. We've got a double bond there. Look up oxygen's electronegativity. It's 3.4 and 3.4. Well, if they're the same number, when we subtract, it must be 0. And that must mean that we have a pure covalent bond. I would probably just label that as a covalent bond moving forward. Again, nothing special about that one. Now, if we had a bond with HO, and you're probably thinking H and O can't bond and satisfy the octet rule. We're just sort of looking at, say, a portion of a bigger molecule. And that's how you do. You can sort of dissect molecules and just look at part of them. So hydrogen is 2.2 and oxygen is 3.4. So we subtract those two and we come up with 1.2. And that puts us into our polar covalent region. That means it has a dipole. And of course, you want to draw the dipole. So back to the molecule there, we put the arrow pointing towards the oxygen end. So that has a negative end. So it's going to attract other positive molecules flying around in solution. In fact, if you've ever seen the meniscus on a glass of water, water has a dipole. So really what's kind of happening here is say an a water molecule is trying to fall over the edge and get out of the glass. Well, it's like other hydrogen molecules are kind of hanging onto it and vice versa. So they're sort of hanging onto the other molecules and not letting them escape. Right, so with that, you can get going to the homework sheet and complete that, and answers are posted.